Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thank you very much for inviting me to talk here. It's been a fantastic workshop so far. And what I'm going to talk about is how to train large-scale linear SVMs when data does not fit in memory. Right? And this is joint work with Shin Matsushima, who was a visiting student from University of Tokyo, and Alex Smola, who is a long-term collaborator and friend, who is currently at Google. Okay. So let me start by setting the scene, and Kirti already did a very good job of overviewing the different types of methods and really made my life a lot more easier. I was sitting there deleting slides from my talk because it already covered a lot of things that I was going to talk about. So the basic setting that you have here is that you have some kind of a, data set, right? And you have some labels on them. I'm just going to keep things really simple and just concentrate on binary classification. Right? So there's a prototypical problem in machine learning. You're given a bunch of points. I need to figure out how do you point with this thing. Okay, doesn't matter. Okay, actually, in fact, I might. Thank you. So you have a bunch of points. They're labeled +1 and -1, and what you're interested in is I'm interested in finding a linear decision boundary, right? So I want to find something that classifies them, and this is linear. One thing I do want to point out is that you will notice that the linear decision boundaries that I'm looking at do not have a bias. Okay, so there is a reason for that because it makes the optimization simpler, and somehow my life will get simpler because of this decision, right? And it's usually not a big deal because you can just add one extra coordinate to your data and more or less get the same effect. Okay, and if you believe in the large margin principle, which many of us do, it simply says that among all possible hyperplanes that can separate these two clouds of points, try to find the one which actually has the largest margin of separation, right? So which separates these two clouds of points with the largest margin. So if you do a little bit of math, and this is fairly straightforward to do, then you will see that this problem can be written as follows, right? So you can write this problem as saying I want to maximize my margin, but at the same time I want to ensure that all my points actually lie on the right side of the decision hyperplane, right? So this is and if you write this out, this is called the so-called primal problem. Okay, and this is called the hinge loss. One of the nice things about this problem, of course, is that it is convex, but one of the bad things about this problem is that it is non-differentiable, right? So you can see the hinge loss is not differentiable here. So amongst other things, you can potentially go the primal route, use the fact that these are convex functions, and so in some sense they are nicely behaved, and do a bunch of things here, for including things like stochastic gradient descent or bundle methods or any of these other potential solvers. But there is also merit in sort of taking the same objective function and dualizing it, right? And when you dualize it, you realize that the objective function that you get out of the dual actually is smooth and differentiable. Okay, so it is convex, smooth and differentiable. So it's actually it's actually a sort of really nice problem to work with. Another thing that is useful is that although you have actually gone to the dual, you have not lost anything, because at any point of time, if I give you the dual solution, you can always go back to the primal, right? So there is nothing that you have really lost by going to the dual. And of course, another really nice thing that you observe is that the objective function becomes quadratic. Okay, so it's a nice quadratic objective function, as you can see, and it is subject to linear constraints. So your alpha i's are between 0 to c. So it's really, the constraints are really simple. The objective function is really smooth and nice and quadratic. I mean, there's not much more that you can really hope for from this problem. Yep.
Just a question. I mean, if you include the bias term, there is a linearity quality.
Exactly. Right. So.
That makes life a little more.
Yeah, so that's exactly the reason. That's a very good point, and that's if you remember, I told you right at the beginning that I'm not including the bias. If I had included the bias, what would have happened is that I would have to add an extra equality constraint here, and roughly speaking, in an intuitive way, the way to think about it is the equality constraint couples all the variables together in the constraints. Right, and that makes life a little bit more harder. Here what happens is that in some sense the constraints are sort of decomposable. So you just have individual constraints on individual alphas, so the constraints don't interact with each other. But if you had that linear term, then there would be some interaction between the constraints. Okay, so that makes life a little bit harder.
Because if you just look at this problem, this is essentially a bound constraint least squares problem.
This is a bound constraint quadratic programming problem. Yes, it is. Yeah.
Justification in dropping the bias term?
Yeah, so the justification usually is that I'm interested in linear SVMs, and in linear SVMs usually they work well when your data is really high dimensional. And so if your data already is high dimensional, you can more or less add one extra dimension to the data, right? And the only effect that you get by adding this one extra dimension is that dimension is also occurs in this, so you pay the price for that dimension also in the primal. So there is a very subtle small change that happens. So in the normal SVM case, you do not regularize the bias. Here you also regularize the bias. That is the only small change. But for all practical purposes, you don't see a big difference, at least for large sparse data sets. You don't see a big difference in the performance.
So the only subtlety there is that you would often need to cross-validate over that parameter.
Yeah.
Typically, your optimization should consist of, your timing should consist of all the different runs, and you should compare them.
So that is only if you are including the bias and not regularizing it, right? So here already the like if you are already including the bias as an extra parameter, then you are already regularizing the bias. So it is.
But then you will need to, what is that constant that you will put in? Often just putting a 1 is a very bad idea. You want to put something that is on the scale.
Yeah, I mean,
so doing the cross-validation will mean you'll need to solve this optimization problem 10 times or 15 times or whatever.
No, I don't. I mean, we'll talk about this offline. Dropping the bias really is not a big deal. Okay, so for large data sets. Okay, so now this is a simple. And by the way, I mean, many of the things that I'm going to talk about really don't matter as much on whether you have the bias or not, right? So many of the things can just carry over. So I'm not, so don't get so hung up about not having the bias in there. That is not the main point of the talk. Okay. So if one of the sort of simplest ways to solve this problem is to say, okay, let me go and do coordinate descent. Okay, so this is basically the dual coordinate descent that Kirti was talking about. So you have a nice quadratic objective function. Here is a little visualization which shows you a quadratic function in 2 dimensions. And so what you can do is you can slice along one of the coordinates, right? So if you slice along one of the coordinates, not very surprisingly, you will see a quadratic function. Okay, so. And of course we all know how to optimize a quadratic function, right? So you can optimize this quadratic function in 1 dimension and you can find the optimal solution, okay? And of course if the optimal solution lies outside the boundaries, you just clip it. If it lies inside the boundaries, you just accept it, okay? At that point you go again and you slice the objective function again along the second axis. And again, not surprisingly, you will find another quadratic function. This is also a 1-dimensional quadratic function. You can go and minimize this and keep going this way, okay? And this is basically what happens when you're doing coordinate descent in the dual. So the coordinate descent in the dual strategy is simply saying you restrict your attention to exactly one of the coordinates, right? To one of the variables. So in this case, let's say you pick an alpha and you write out the objective function only in terms of alpha and keep everything else constant. Okay, and now you can see clearly that this is a quadratic function in alpha, right? So you have an alpha t square term here, and then you have an alpha t plus some constant term here, and then there's minus alpha t and a constant. So clearly this is a quadratic function, and this is subject to linear constraints. So if I give you such a 1-dimensional objective function, more or less from your high school algebra, you know that the way to solve this is you take the gradient, set it to 0, and in fact you can find a closed form solution. Okay, so if you want to clip it between 0 and C, so you just take the median between 0, C and the solution, and that becomes the updates that you do. Okay, so the nice thing about the overall objective function is that it is quadratic. It has bound constraints, so you can actually find closed form solutions. So every time you can pick a coordinate, you can find closed form solutions. Okay, so this is the really nice thing about this particular objective function. Of course, if you had the bias term in there, you would not be able to do this for one alpha. You would have to pick 2. Okay, so that's the only thing, but more or less exactly the same thing works. Okay, yep.
Just because, can you actually map this 1D to a function to its primal and have interpretation like this?
Yes, I'll talk to you offline about it. There's a very, very nice interpretation which says that if you actually do these updates, they are very, very closely related to stochastic gradient descent updates, but sort of you're doing the right stochastic gradient descent updates. So I can talk to you more about that. Okay. So any questions so far? Right. So I'm just setting the scene. I mean, I haven't told you anything really new yet. Okay. So now, see, the problem is that as we, as Kirti said, we are collecting lots and lots of data, and as we are collecting more and more data, we want to solve larger and larger problems. Okay, and usually we are getting to the place where we are not able to fit the entire data into RAM. Okay, so the people have of course started looking at this problem, and we are not the first ones to look at this. And there's a paper in KDD 2010. So this is the best paper award at KDD 2010, and the idea there is very neat and sort of very simple and intuitive. They say, well, if you're going to do coordinate descent anyway, why don't we do the following thing? Let us split our data into blocks. Okay, so let's say we take, suppose you have 2 gigabytes of RAM, so let us split our data into blocks which fit into 2 gigabytes of RAM. Okay, and then we compress all these blocks and store them separately. Okay, so we sort of take each block, read it in, we compress it and then put it back to disk, and then you sequentially go through each one of these blocks one at a time. You load those data points, then you will get a set of alphas, and you optimize only those set of alphas. So basically you restrict, it's basically block coordinate descent. So you take a block of data, you optimize over that block. When you are done with that block, you throw it back, you pick another block, you optimize over that block, then you throw it back, and then you pick another block. Right? So this is a really simple idea that you say you take one block of data at a time, and you read it, and you optimize over it. Okay. So there was a follow-up paper in KDD 2011 where they do exactly the same thing, except with one twist, which is they say, whenever I take a block of data and then I optimize over it.
What is the advantage of that? Why was it best paper? What's so neat about that?
Oh, the only neat thing about it is that you could actually train, like even though you had a laptop which only had 4 gigabytes of memory, if I gave you a 100 gigabyte data set, you could still train. So that was the neat idea. Okay. So the sort of follow-up thing was to say that what we are doing every time when we are taking one block of data and we read it and we optimize over it and we throw it back, is somehow we are not storing information, or we are not sort of keeping enough information from the past. So what we should be doing is that every time we should retain some so-called informative samples. Okay, so roughly let me show you a cartoon to show you what are informative samples. So
one quick clarification. So these blocks, are they a bunch of XIs, or are they blocks of the kernel matrix?
No, there's no kernel. Everything is linear. So it's only data. So you take a block of data,
Some selection of XIs.
Yeah, some selection of x's and the corresponding alpha is. So you see, we are always doing dual, right? So for every x there is an alpha. Okay. So sort of roughly this cartoon tells you what are informative samples. So if suppose this is your current decision boundary, then points which are close to your decision boundary are roughly more informative.
Sorry to keep it running.
Yeah.
I thought you said they were blocking of features.
No, on data points. So this is
not block coordinate descent in that sense.
It is block coordinate descent in alphas. See, every data point corresponds to alpha. So now I'm always in the dual space, right? So every data corresponds to alpha. So you're only doing block coordinate descent in the alphas. Okay. So the informative samples are roughly the ones which are close to the decision boundary, and the points which are say very far away from the decision boundary are sort of not very informative, right? So maybe they're not going to influence your decision boundary as much, so you should be throwing them out. Okay, so this is the basic idea. I mean, of course I'll make this a little bit more formal as we go along, but this is the intuition, or this picture is what you want to keep in mind. Okay. Now if you look at these methods, there are some significant drawbacks, right? So what is the first drawback? So the thing is that they both do the splitting of data into blocks and then they compress the blocks. Okay. What this means is that even before you begin training, you have to load your entire data set at least once and do some processing on it. Okay, and this is usually wasteful. I mean, usually if your data set is very large, then you're just taking a lot of time just to load your data at the beginning and compress it and store it back. And the other thing, which is the bigger problem, is that whenever you're loading data, you're not training. And when you're training, you're not loading data. So in other words, when your I/O is busy, your CPU is idle. When your CPU is busy, your I/O is idle. Right? So there's a sort of they interlace I/O with CPU one after another, and that is usually the problem. Okay, and if you know a little bit about systems, it's fairly clear that disk I/O is very slow compared to CPU. Right? So usually it's order of 1 to 100, depending on where your disk is, how fast your disk is, whether you have a solid state drive or a hard disk, or whether your data is living on the network and you have to read over the network. So it could be up to a factor of 100 slower than the CPU. And the other thing is that you really want to be not doing random access on the hard disk, and you really want to do sequential access. And this is actually something that you may not realize, but even in the RAM, doing sequential access is 10 times faster than doing random access. So even though the name is RAM, it's a misnomer in some sense. So even right from the RAM, hard disk, solid state drive, and on the network, at all levels, if you can do sequential access, you're always much better off. And the other thing that we were wondering is that can we, because these multi-core processors are becoming more commonplace, can we use multiple threads in the training, and how can we exploit all of this? And somehow my goal is that I want to keep both I/O and CPU busy simultaneously. So that is the goal that I have. Okay, clear? Questions? Okay, so
already these Pegasus type of algorithms are streaming, right?
Yes. So I'll come to that. We'll talk about it. So let me show you our architecture, and then I'll show you why not Pegasus. Okay, so why not stochastic gradient descent? Okay, so here is the architecture. Okay, the architecture is simply saying, why don't we do the following thing? I mean, this is a really simple idea. The idea is that you have two threads. Okay, so you have a reader thread and a trainer thread. What the reader thread does this is basically it does in its entire life is it goes through the hard disk and reads data from the hard disk and it throws it into the RAM. Okay, so you have a cache, what I call a working set, and the reader constantly reads data from the hard disk and throws it into the RAM. And what the trainer does is it constantly goes through points in the working set. It updates the parameters. It does training on the it updates the alphas and the weight vectors, and whenever it finds a point which is not informative, it throws it out. Okay, and this cycle continues. Now, if you think about it, this is basically we are not doing something really fancy, except for one thing, which is that whenever the trainer finds a point which is not informative, it throws it out. Okay, so why is this significant? Because suppose if you were doing something like just going through the points in the RAM one after another, what would happen is that, say, by the time the reader has done, say, one read of the data through the hard disk, the trainer would have done roughly 10 times updates, let's say 10 to 100 times updates, right? So by the time you have done a read of n points, you would have done about 10 times n or 100 times n, roughly in that range of updates. However, by throwing out points which are not informative, what is happening is these 100 n updates are being concentrated on the important points. Right, so they are really, you're working on the sort of points which are useful or important for your solution. You're not working on the points which are not going to be useful. If you were doing stochastic updates, you'd just be randomly sampling points. Okay, and this is one of the really big advantages for doing dual coordinate descent as opposed to stochastic gradient descent. In stochastic gradient descent, you cannot decide whether a point is important or not. Every point is as useful as every other point. So the only thing that you can do is you can do uniform sampling over the points. The moment you go to the dual, one of the very important viewpoint shifts happens, and you realize that you can place some kind of a distribution over your points. You can say that some points are more important than the others because you can look at the, roughly you can look at the norm of the dual gradient, and based on that you can say that some points are more important. So this is like doing importance sampling. I mean, I use the term very loosely, and I'm sure many statisticians in the room will be offended, but it's roughly you're concentrating your attention on the useful points rather than on every point. Okay, and I'll show you this leads to really dramatic feedback.
Compared to like Ratty Sebro's, he had lost NIMs, not ICML, where he was maintaining distributions on STD.
No, I haven't looked at that work, so probably will, you can point me to that. Yeah, there was another question?
Why don't you just look at the primal loss for that?
Sorry?
Why can't you just look at the primal loss of the existing working set for that, for the starting point?
Because if I do things in the primal, I do not have this natural sort of distribution. I cannot figure out which point is important, right? So the dual gives me immediately this importance of a point, right? That is the beautiful thing about the dual, which the primal does not give me. Right? In stochastic gradient descent, it is very hard to decide that, oh, I don't want to train on this point. In dual coordinate descent, it is trivial. Right? Yeah.
Stochastic gradient descent also, like if your loss is 0, then you don't train on the point.
But you still have to read the point, right? And
that you have to here.
just having the loss 0 is not enough. The KKT conditions have to be satisfied, right? So that is in the dual it's much more. I'll show you the equation, right? So in the dual it's much more easier to decide rather than in the primal.
So one danger is in the beginning you will get 8 points, and your importance evaluation will be wrong.
So I'll show you how we can tune it automatically. So at the beginning, what you would want is you would want to be more conservative and say, I want to keep more points.
From the beginning.
Yeah, of course I want to throw away points from the beginning, but I want to be more conservative at the beginning because I want to say, I don't want to be misled. But as I'm coming closer to the solution, I'm more confident about my solution, so I can throw away points more rapidly. So, and I'll show you how this tuning happens automatically in our case.
But you could get very bad points in the beginning. There's no, one range to get only the good one.
Yeah, but you can recover from it. I'll show you how you recover from it.
Because you can tell the reader to get back those points.
Yeah, see, that is one advantage, right? Even if I throw away a point, the reader will eventually come back and revisit that point. So the point will come back.
It's not a strictly streaming setting where you won't see that.
Yeah, I will see the point again.
You make only one pass through the hard disk.
No, I'll do multiple passes through the hard disk.
So you do a second pass.
Yeah, I'll do a second pass, and in that time I'll see the point again. Right? So the reader is constantly going through the points in the hard disk. Okay, questions?
You're not assuming it's separable, right?
Sorry?
The data aren't separable.
No, this is soft margin. Yeah.
Because I think the better the data set looks, the easier it will be not to make these kinds of mistakes.
Yeah, but okay, so maybe it may make sense to actually look at the separation condition, but before we go on, any other questions? I'll show you
Should the reader also maintain some important sample?
No, the reader is a very dumb reader in our case. So the reader just constantly iterates.
Should it?
No, because the trainer has enough information to figure out which points are useful, right? So
But I'm saying if the reader does it, then you don't even get those points from the hard disk.
No, the reader always reads from the hard disk, and we want always sequential access, right? We do remember we do not want to do any random access on the hard disk. That is that is a strict no-no for us.
So one implementation issue. These things typically tend to work well when you randomize your data. Data coming in and all your negative, this would be trouble.
See, okay, if you have all positive and all negative, everybody including stochastic gradient descent and dual coordinate descent will fail. But however, if you just take one random like permutation of the data and then run stochastic gradient descent and just keep using the same random permutation again and again, for stochastic gradient descent, the convergence is terrible. While for dual coordinate descent, that is not. I'll talk to you. There are lots and lots of very cute little observations like that. Okay, so sort of here is the philosophy which says that you iterate over data in the main memory while you're streaming data from the disk, and you evict primarily examples from the main memory that are uninformative. I think Alex was watching too much Big Brother or some such show, so he wanted to use the word evict, and he insisted that we have to use the word evict. So, it's like being evicted from the Big Brother house. So they evict primarily examples from the main memory and that are uninformative. So basically you're concentrating your attention or all your CPU on the informative samples. Okay. So the code actually turns out to be so simple. I don't know why this projector seems to eat away all my red colors, so my reds are not projecting. But anyway, so the code is so simple, and literally this is the pseudocode which is transcribed from the C code, right? Which is the implementation. So basically, the reader just goes through points in the disk. It selects a point, right? And first it checks if the cache is full. If the cache is full, then it randomly picks a point and deletes that point and throws the new point in. Okay. If the cache is not full, then it will read a point from the disk. It will calculate the XIXJ, the dot product, because you need this in the updates, and you store this in the RAM, and it updates the active set size. And if the reds were actually showing, you would realize that this and this are the only two places where you need a lock. Right? So there are only two operations. When you add a point into the active set or when you delete a point from the active set is the only two times when the reader has to lock. So there's very, very little synchronization between the reader and the trainer. So they are never bottlenecked on each other. Right? So that's one advantage. And here is how the trainer looks like. So what the trainer does is it computes, so it selects a random point from the RAM, okay, and then it computes this gradient, the dual gradient. Okay, and then this is the condition using which it decides whether the point needs to be thrown away or whether it needs to be kept. So roughly what does this condition say? It is very similar to the shrinking condition that is used in training SVMs. So the condition says that if the alpha for a point is 0 and the point is very well classified, which is where well classified means the margin is at least epsilon, okay, and I'll tell you in a minute what epsilon is and how we tune it. If the alpha is 0 and the point is really well classified, or if the alpha is equal to C and the point is really badly classified, where the gradient says it's less than minus epsilon, then this point is very far away from the decision boundary and you should throw it away. Now what is this epsilon parameter? The way we decide this epsilon parameter is by looking at the absolute value of the past gradients. Right? So if you think about it, our updates are going to move things by at most the dual gradient, right? And we look at the absolute value of the past gradients, the historical gradients, and using this max value, we decide the value of epsilon. So roughly what happens is at the beginning, because you are very far away from the solution, your gradients will be all over the place. So the max gradients will be very, very large. As you are converging, one of the signals that you want to monitor or by which you know that you are converging is that the absolute value of the gradients must go to 0, must converge to 0. So as you are going down more and more in the optimization, this epsilon will shrink. And if the epsilon shrinks, you will become more and more aggressive about throwing out points. So at the beginning, you are very conservative about throwing out points. You want to really keep all the points as much as you can. As you are converging towards the solution, your epsilon shrinks down to 0 and you automatically throw out points. Right? So this is the automatic tuning that happens. So at the beginning you are conservative, and then later you really start throwing points down. Okay, and then once you have decided whether to keep a point, if you want to update it, you do the update, you maintain the alpha and the W, and then you maintain the epsilon and you keep going through this. Okay, and also we have this one other condition, which is if the cache becomes more than 90% full, then we'll start becoming a bit more aggressive about throwing out points. Okay, so that's another thing that we do.
Model alphas be 0?
Yeah, the alphas can be 0, but then the gradient has to be bigger than epsilon. So in other words, you have to have the alpha being 0 and the point being well classified.
So you won't throw out all points which are not 0?
No. So you remember that cartoon that I had, this one, right? So you'll try to keep not just support vectors but points around this region, but maybe you may throw away this point and that point because the alpha for this point is 0 and the gradient is very large, right? So Okay, and let me just tell you that I'm running out of time, so I'll just tell you that you can prove convergence. Okay, so although we cannot prove rates of convergence, we can show that this whole scheme converges. So I'll probably not bore you with the details of how the convergence happens, but let me show you the interesting thing, which is the experiments. Okay, so although it's a very simple idea, we wanted to test this on a variety of data sets and sort of across a range of values of data sets. Okay, so here are four data sets that we looked at. So they are data sets which vary in the number of data points. So n is the number of data points. So they vary between 350,000 data points up to 50 million data points. Okay, they also vary in the number of dimensions. So we have 800 dimensions and going all the way up to 30 million dimensions. They vary in the sparsity patterns. So here OCR is a very dense data set, it's 100% dense, DNA is 25% dense, web spam is reasonably sparse, and KDDB is extremely sparse. So across a variety of sparsity patterns and across a variety of class balance. So you see this OCR is reasonably well balanced, while on the other hand DNA is extremely imbalanced. So there are very large number of plus points versus compared to the minus points. Okay, and they also occupy different, they all are of different size. So starting from 5 gigabytes going up to about roughly 63 gigabytes. Okay, so these are the sort of data sets that we worked with. And the very first question that you want to ask is, does active eviction work, right? So if you just did, why not do just random, why not just do random updates and then the reader just randomly throws things out? This is to answer Pratik's question, and here is the plots which show you that active eviction actually significantly helps. Okay, so this is random prediction, this is just random eviction, and this is active eviction, and you can see this is orders of magnitude faster. Okay. And by the way, all plots are basically relative function value difference, which means they tell you how far away, so dual minus optimal dual over optimal dual. So that's the relative function difference, and this is wall clock time. Okay. The next question we wanted to ask is, okay, how do they actually how does this strategy of reading data continuously from the disk and updating compare with these methods like block minimization and selective block minimization, which retain informative samples? And here you can see this is an example. Unfortunately, I don't know why my reds are not showing up, but this is our StreamSVM. This is block minimization and this is selective block minimization. So you can see this initial offset that they have is the time that it requires for block minimization and selective block minimization to read the data, to compress it, store it back in disk, and then start reading it again and again. And even before they have done this one pass through the data and pre-processed it, we more or less have converged. So I think we are roughly somewhere here. So I can give you a solution which has about relative function value difference of 10 to the minus 5 even before these methods have even started reading their data. Okay, started their training. The same thing happens in web spam. So again, more or less the same story repeats here. In KDDB, interestingly, the same story doesn't repeat, right? So it turns out that StreamSVM is comparable to block minimization and selective block minimization, and we were wondering about this for a long time, and then it turns out there's a reason, there's an explanation for this. The reason is, if you look at KDDB, it has about roughly each data point has about 100 non-zero entries, okay, and the size of the data vector is 30 million. Okay, so when you're doing updates in the RAM, you have to access 100 random locations out of a vector which is 30 million long. Okay, and of course because this is random access, it is not very good. It takes time. On the other hand, the reader is very fast, because for each data point it only needs to read 100 numbers from disk, right? So the speed of the reader and the speed of the trainer are reasonably comparable in this case. So therefore you don't see that big effect of. We are using a sparse data structure, but for the weight vector is stored as a 30 million dimensional dense vector, and then you're accessing randomly 100 points in there. So even in RAM, doing random access is actually very slow. Okay, and on the other hand, the reader is reasonably fast because it only has to read 100 numbers. So these are all, I think, with 2 gigabytes of RAM. So everything is with 2 gigabytes of RAM. And here is, so I'll also show you experiments where we tried different values of the RAM. So these are all with standard 2 gigabytes RAM. And then here is another set of experiments. So this is with DNA, and again the same story repeats. And this, so far I've showed you just one value of C. And this is something that, I do want to stress that when people propose optimization algorithms, they must test it on different values of C. Usually I see these papers where they say, oh, we propose this new optimization algorithm, and what we're going to do is use a hand-tuned value of C, which is found from cross-validation, and hey, look, my method works very well. But as an optimization algorithm, you have to work well on different values of C, right? In some sense, you are not, you shouldn't be just looking at one hand-tuned value of C. So here is how things work for different values of C. So this is for C equals 1, and if you increase, and this is intuitively, if you think about it, as C increases, the problem becomes harder. And you see that things like block minimization and selective block minimization really struggle with it. Block minimization has not even converged anywhere for C equals 10, C equals 100, both of them are more or less not there. For C equals 1000, the same story repeats. Okay? So that's one thing that I do want to point out, that please, if anybody in the audience is proposing new optimization algorithms, please validate them for different values of C. I mean, that's a good point. And here is an experiment which shows what happens when we vary the cache size. Actually, if you see, if you increase the cache size, the performance doesn't seem to be all that much different. Although if the cache size is very small, this is 256 MB. So for 256 MB, the performance is bad, but beyond that, everything else seems to be more or less in the same ballpark. Again, the reason for this is that if your cache intuitively is big enough to hold the active size or sort of the important points, then it's fine. I mean, whatever size of the cache you use, beyond that does not seem to help. Right? So, but if your cache is smaller than the size of the active size, like for instance, if it's only 256 MB and your active size and your data doesn't fit in, then in that case, having extra cache doesn't seem to help. Okay? In fact, in some cases, you get a slightly worse performance. Okay? And here is another experiment that I want to show, where what we do is we take the DNA, we read the DNA dataset, and then we do an expansion, we do a feature expansion on this dataset, okay, and then we train on this. So if you do a feature expansion, DNA is a string dataset, so basically you compute the set of all possible substrings of the strings, and that gives you a dataset which has 12 million dimensions, 50 million data points. On disk, it would take about 3.5 terabytes of data. That's what it would be. Here so basically we can push around 3.5 terabytes of data with about 32 gigabytes of RAM on a single machine with 2 threads in under 8 or 10 hours. Okay, so that's the kind of performance that you can get. And to conclude, there are a bunch of things that I did not talk about. The idea can actually be extended to take into account other storage hierarchies. So you can exploit things like solid state drives and so on and so forth, which are intermediate between the hard disk and the RAM. And even in the RAM, you can potentially use the L2 cache in the processor and the RAM separately. So we are looking at some of those. I haven't shown you how to train on multiple machines simultaneously. This is something that we are actively looking at, and if you have ideas, please talk to me. Sorry, this is about the multiple machines, and then about training multiple models. So this is something that if you have really large data, one of the things, your dominant cost is I/O. So if suppose I want to know how my model performs, say for 4 different values of C, I shouldn't be loading the data 4 times and training 4 times. In one shot, as I am reading the data once, I should be training 4 models simultaneously and getting my 4 models for 4 different values of C in one shot, because the dominant cost is the I/O, so I don't want to be doing I/O multiple times. So we have some ideas on how to train multiple models simultaneously. And of course there are extensions to other problems. For instance, I didn't talk about logistic regression, where something like the shrinking condition does not exist, but we can actually, we came up with a new condition which is similar to shrinking, and we can do logistic regression on these scale data sets as well. We're also looking at multi-class problems, and about structured output problems, there's still a lot of work to be done because the label space there is very large. There's a paper that's going to appear in KDD The code will be available in a day or so from Shin's homepage once we track down that last memory leak that Valgrind seems to be spitting out. We will release the code. And finally, I want to acknowledge my co-authors. That's Alex Smola, who's a long-term friend and collaborator, and that is Xin Matsushima, and you can see he's advocating that we all use dual cache loops. Thank you very much.
Thank you. Quick question or two?
Questions? Everybody wants to grab coffee? Yeah.
So my question is kind of related to what Manik asked. Is data segregation, label segregation helpful in dual coordinate methods? Because if I'm not wrong, Linear actually does that deliberately.
What do you mean by label segregation?
You take your data, sort it so that the clusters come first.
No. Nobody does that. No.
Oh, Linear does it actually.
No. No. You wouldn't do that. I mean, on the contrary, you want to take your data and randomize it. Yeah, you always want to randomize it, and if you're doing stochastic gradient descent, in fact, you want to randomize it at the beginning of every iteration. So I have some plots where if you just take data, you randomize it once, you run stochastic gradient descent multiple times, your convergence will be slow. But on the same data set, you take and you randomize it at the beginning of every iteration, your convergence will be significantly faster.
Maybe I will take this offline with you.
Yeah.
This is something I had.
Yeah.